Welcome to EDU World Space.
Problem 8.49 is about neutron moderators. A neutron moderator is some scheme for reducing the speed of neutrons. This is used in nuclear reactors, for example. This particular problem tells us that the Canadian nuclear reactors use a heavy water moderator, but they're also used for various types of experiments involving imaging and other types of things using neutrons that need to be moving slowly. But in this case, we have a heavy water moderator, and heavy water is water, H2O, except the hydrogen atom in that has an extra neutron in its nucleus, which makes it heavier. And a hydrogen atom with an extra neutron in the nucleus is called deuterium. So the first thing we want to know is, as a fraction of the initial velocity, which we're not told a specific number, which in this case we don't really need to know, what is the fraction of that you end up with after one of these collisions if it's coming head on to it and it's elastic? And then we want to know what the ratio of the kinetic energy is. And then we'd like to figure out how many collisions it takes to slow the neutron down by a factor of 59,000. So for the elastic collision, we can use equations 8.24 and 8.25. So if you want to find out how you get to these, you should go back and look at them. But briefly, it uses both the conservation of momentum and the conservation of kinetic energy that occurs in elastic collisions to find the final speeds of both objects. It gives you your second equation, so you have two equations and two unknowns. And so using that, if we let this be A in those equations, we see that the final speed of the neutron is going to be the difference of the masses divided by the sum of the masses times its initial speed. And so since we want a fraction of velocity of speed that's left, we take this, and then this is 1, this is 2, so this is -1, this is 3. So this is -1/3. So the neutron bounces back right in the direction that it came. It's the negative sign here, and it's moving 1/3 as fast as it was before. Now, what is the kinetic energy of the neutron after that? So the initial kinetic energy is 1/2 m the initial squared, and this is going to be equal to 1/2 mn times Vn final squared. Now we know that this is that the ratio of these is well, so this is the initial and this is the final, and we want to divide the final by the initial to get the final divided by initial kinetic energies. So all the 1/2 m's cancel out. And so the final squared divided by the initial squared is equal to the ratio of the kinetic energies. And since this is the same as the ratio squared, this is 1/9. Now, to figure out how many collisions we need to have to get this reduction in the speed, we see that every time there's a collision, there's a constant factor by which the speed is reduced. And so that means that the final speed is going to be, after n collisions, is going to be 1/3 to the n, because you just multiply by 1/3 every time there's a collision. The initial. And so we want v final divided by v initial to equal this 1/59,000. Again, this is 1/3 to the n. And so just rearranging this, we see that 3 to the n equals 59,000. So we want to figure out what exponent n we need here to get 3 equal to 59,000. And of course, whenever you see something like this, you take the logarithm of both sides, and then you get what you're looking for. So you could take the base 3 logarithm of both sides and immediately get what we're looking for. But since I don't think that many calculators, for example, allow you to necessarily choose the base of the logarithm you're taking, you can actually take the logarithm to any base you like. So n times log 3, and this is because the logarithm of a number raised to any power is that power times the logarithm of that number. And here it doesn't matter what the base of the logarithms are. There's the logarithm to the same base of our 59,000. And now if we were using base 3 logarithms, the logarithm to the base b of b is 1, and then have this to the base 3, and you'd get the answer directly. Or the change of base formula, of course, is if this is like a natural logarithm, for example, you divide the logarithm to the whatever base you happen to have of one number by the logarithm to the base you happen to have of the number you really want the base for, and then that does the change of base for you. So however you'd like to evaluate that, you end up with 10 collisions being required, because 3 to the 10th is 59,000.